Our goal over the next few slides is to develop relationships between the pressure and the temperature for each of the three-phase equilibria. Since the approach is the same for the liquid-vapor, solid-vapor, and solid-liquid phase changes, we will just consider a generic transformation between two phases called alpha and beta. The method we will follow consists in obtaining an expression for the slope dp over dt of the coexistence curve, and subsequently separating the variables p and t and integrating these differential expressions of p and t to obtain our desired relationship between the pressure and the temperature along the coexistence curve. Let us first use our statement of the second law of thermodynamics to indicate that at the temperature T and pressure P, the two phases, alpha and beta, are in equilibrium. In the preceding lecture, we stated that two phases are in equilibrium at some temperature and pressure if they have the same molar Gibbs energy. So we write Gm alpha at T and P equals to Gm beta at T and P. Let us now consider the same equilibrium at a slightly higher temperature, T plus dt, where dt is small. For the equilibrium between the two phases to be preserved at this new temperature, that is, for the state representing the system to be on the coexistence curve, the corresponding pressure must be equal to P plus dP, where dP is shown on the adjacent plot. A value of dP larger than that shown on the plot would lead to our substance being present as alpha phase only, while a value of dP smaller than that shown on the plot would lead to the beta phase as the only stable phase. So equilibrium in the new state with temperature T plus dt and pressure P plus dP implies a very specific relationship between the temperature change dt and the pressure change dP. Equilibrium in this new state is expressed as Gm alpha at T plus dt and P plus dP equal to Gm beta at T plus dt and P plus dP. We can now define dGm alpha and dGm beta as the changes in molar Gibbs energy for the alpha phase and the beta phase as a result of the temperature and pressure changes. Since the molar Gibbs energy for the alpha phase is equal to that for the beta phase at both Tp and T plus dt, P plus dP, then the associated changes dGm alpha must be equal to dGm beta. Next, we recall the important result derived in a previous lecture that the molar Gibbs energy depends upon temperature and pressure according to dGm equals Vm dP minus Sm dt. Applying this equation to the alpha and the beta phases yields dGm alpha equals Vm alpha dP minus Sm alpha dt, and dGm beta equals Vm beta dP minus Sm beta dP. Note that different phases of a given substance generally have different molar volumes, different molar entropies, and different molar enthalpies. Combining the last three equations leads to the relationship Vm alpha dP minus Sm alpha dt equals Vm beta dP minus Sm beta dt, which we can rearrange as Vm alpha minus Vm beta times dP equals to Sm alpha minus Sm beta times dt. This leads us to obtain an expression for dp over dt equal to the slope of the coexistence curve p versus t, and write dp over dt equals Sm alpha minus Sm beta divided by Vm alpha minus Vm beta. This equation indicates that the slope of the coexistence curve is equal to the ratio of the molar entropy change for the phase change to the molar volume change for the phase change. Recalling the relationship between the entropy change and the enthalpy change for a phase change, we write dp over dt equals delta H for the phase change divided by delta V for the phase change times the temperature. This last equation is known as the Clapeyron equation. Over the next 3 slides, applying the Clapeyron equation to each of the liquid vapor, solid vapor, and solid liquid equilibria, we will derive expression for the corresponding coexistence curves.